basic algebra. It supplies us with the ability to record algebraically the transformation of the plane that you might made up. Let me get back to that picture from last time. This one. Okay, so no matter how complex picture is, how it is described through these transformations, you can not only make a picture, which all it takes is just the paint, but also you can describe it algebraically. So this one is, what is this? From last time. So what has happened here? It is flip. It is a vertical flip, right? The vertical flip, and you can see what has happened to x, y. X is on the same. Y is on the same level. Nothing happens to y, and x becomes negative, right? So that's like a generic point, and by tracing only where one point goes, because the transformations are so simple. If you know where one point goes, you know where the rest of them go. So in this particular case, y remains the same, x changes to the negative, or rather you multiply x by -1. So it is a flip, a horizontal flip, which is here on the list, on the right list, number 2. Okay, so that is then the challenge is to be able to go both ways. You have a description. The description is exclusive, 6 items. But you should be able to, well, let's go one way. One way is what I just asked you to do, is look at the picture and tell what has happened. Okay, so only 6 items. Okay, seems like not a lot, but you can already predict that we can have more than 6. How can we have more than 6? Combine. Can you be more? Yes, combine. How can you be more specific?
Like, for example, you could flip about an axis and then also shift it.
Right. Well, so you could stick within each of the you can stay within each of the lists. So you can continue on doing horizontal things or vertical things. So which we already done. So that's not the most interesting thing. You can shift, flip, shift horizontally, flip horizontally, and then stretch horizontally. Okay. So that's like what we have already seen it. It's more interesting when you pick from the left and from the right separately. So for example, the easiest one is 2 shifts. 2 shifts. So let's try to imagine what that looks like. So 2 vertical shift by 2, followed by horizontal shift. Vertical shift, not 2 by 2. So 2 units to the right, to up, and horizontal shift by, say, 3. Okay, so it is literally to be seen as 2 consecutive operations. You can think of these as compositions too, you know. So it is we, for the most part, we looked at compositions of functions with all the functions being numerical functions, though they don't have to be. Any function will do, and the transformation of the plane is a function of the plane, and so ultimately we'll look into that in this from that point of view. But for the time being, we'll just do it one at a time. We don't have too many, but even if you have only 6, you take 2, you already have 36 operations right away. If you just do 2 instead of 1. Okay, so that's the simplest one, shift by 2, followed by vertical shift by 2, horizontal shift by 3. So you don't have to imagine the whole thing at once, but rather I suggest early on, write it up in the algebraic sense, and then follow where a generic point goes. So you have point x, y. Under the first transformation, we'll go take a look back at the list. So vertical shift by 2, as you can see over there at the top, y goes up by 2. Okay, so it becomes x, y plus 2. That's the first one, right? Vertical shift, x remains the same, y grows by 2 the end. Okay, so I'm just doing algebra for the time being. And then second operation, it is a horizontal shift by 3. So once again, I go to the list. Horizontal shift by 3, top of the second list. X changes by k. K is equal to 3. So from here, we go to the next level, x plus 3, while nothing happens to y. So step 2, that is my algebraic transformation. Okay, so if this verbal description that I started with is sufficient, it might be, then you don't need a lot of algebra. Maybe you go the other way around. You might actually imagine what has happened and then you come up with algebra. But you're probably better off doing algebra long term. So I take a generic point x, y, here somewhere, say, maybe here, x, y, and then as you can see, step number 1, I go to x remains the same, and I move 2 units to the right. So once again, generic point x, y. I have already know where my next location is going to be. It's going to be here. X, y, nope. Up. Okay, over here. Right? That's the first step. X, y plus 2. Let me write it here, x, y plus 2. Just watch the coordinates. That's the coordinate x, this coordinate y, this is coordinate y plus 2. Okay, so I have in red, I'm writing my coordinates in pairs next to the point, or I mark the coordinates of each point on the x-axis and on the y-axis. Okay, so you can see what's changing, and there is no change in the horizontal direction at step number 1. Okay, so the next step is step number 2. X changes, y does not. So I'm still at the level of y plus 2, and I move 3 units to the right. So that is my what is it? X plus 3, and this is my shift. Okay. So you can see what has happened. You can see those arrows. They they depict exactly what has been described. 2 units up, 3 units 2 units up, 3 units right. Okay. So if an arrow points down, we're going down, and so on. So that all we need to do. But if you imagine that what has happened to one point, now you can imagine what happens now, and that's the key. What has happened to the whole plane, right? So the description certainly applies to the whole plane, and once again, I'm suggesting that you should probably imagine like two pieces of paper, or like a transparent piece of paper or plastic with XY plane printed on it, and it slides above the original XY plane, so you know where you are relative to the original position. So what you see here is the original position, and then you just shift it. Shift or whatever other operation you might have to carry out. Okay, so a piece of paper shifted like this and like that. That's all. What if I flip the two? Flip meaning flip the order of operations. So switch the order. What's going to happen? Switch the order. So step number 2, then 1. Same steps in the opposite order.
It'd be the same outcome.
Ariel, can you explain?
So if we start off with the second step first, it would go from that first plane, it'll go 3 over.
Right, to the right, like this, right? Oops.
Right. And then if we do the first step after that, it would just rise up 2 spots,
Yeah.
leading to the same point.
Okay, so that's the alternative order of producing the same outcome. Okay, so it is not atypical when you pick 2 from 2 different from the 2 columns, separate different columns. So because the change of x or change of y, if you switch the order, the result will be the same. So it's a convenience, even though you have to be careful because if you do it from the same column, doesn't apply anymore. Remember, shift and stretch. If you flip, the result might be the same. So it's only when you pick horizontal and vertical separately, then it doesn't matter. You can sort of move them together, horizontal and vertical, and then deal with them separately. So that makes your life slightly easier. But you can imagine the variety of transformations that you can produce in that matter. So I only took 2 out of 36 pairs. So I could, for example, the next one might be what? How about a flip? Flip vertical, flip horizontal. Step number 1. And step number 2, how about stretch vertical by 2. Okay, once again, it is a description of what's happening to the XY plane. It is as if it is a piece of paper once again. So if you're not sure, if you cannot imagine that in your head, just take a piece of paper and do it with it, and that certainly helps. So any piece of paper that you can see to put it to the light, you can tell what's happening and match it up with the original. So, but we are pursuing algebra here for the most part. Okay, so that is my piece of paper. I once again pick a point, a generic point as I call it, and I see where it goes under these 2 operations. The first operation is a horizontal flip, where I'm gonna go end up. Where will the point land? Go back to the list like this. Okay, so we're doing it horizontal. So flip horizontal, second column, second item. Well, you look at the algebra. So maybe let's do algebra first. The algebra, I think helps. So xy goes to, according to that plan, flip horizontally. So x changes to negative x, y remains the same. That's step number 1. And step number 2, stretch vertically. What's going to happen? Nothing changes to, no changes to x. X is horizontal, y vertical, so it will be still negative x. And what happens to y? Stretch 2y. Okay, so that's it. Only remains to be now visualize it. So negative x, it's going to cross the x-axis. Remember, that's what the flip is. It is a horizontal flip, is a flip about the y-axis. Okay. So the other point is then the negative x y. And then it is stretched by 2. So stretched by 2 roughly. That's where it roughly is going to end up. I'll write it anyway. So visualization of one point at a time has its problems, and that problems is you can see the problem is that the vertical shift in the first example looks exactly the same as the vertical stretch in the second. So if you do it one at a time, you just move the point, but without the rest of the description, you don't know what has happened. So it does appear, look at it, just arrow goes from this location to that. So one point does not really tell you the whole story. It is how do you visualize a stretch. vertical stretch. You probably need like more than at least one more point in order to see what happens. So let me try to do that. Say if I have another point, how should I do it? Let me try it. The shift is okay, right? The shift is okay, and the flip is okay. It is as long as your point is not on one of the axes, you will see what has happened. But the stretch it changes the geometry of the plane, so the distances change. In this particular case, all the distances double. So if you have 2 points, not all the distances double, or the vertical distances double. The horizontal remains the same. So well, let me try. Let me try it this way to visualize the only the second step. This is what's going to happen. So this is my okay. Let me put it this way. So let me make see what will happen to the square. Okay, so the square is plotted on the original plane and the xy plane, and now I'm carrying out the vertical stretch. Okay, so you can still do it point at a time. So if you cannot tell what's going to happen to this square, what's going to happen to this square if you can tell right away from the verbal description. It will turn into a rectangle. Can you be more specific? Right, so it will be twice as long. It will be stretched vertically, literally. So a square will become a rectangle in the direction, stretched in the direction that we pointed out. Okay, so it is stretched vertical, so it will be stretched vertically, but where is it going to be located? A rectangle, so it will be 1 by 2 rectangle. Where do I put it? It will right coincidentally, but it will be right up above it like this. Because the rest of it also stretches, and so the location matters. Let me do a few more examples of what happens to these rectangles. So if I take this rectangle, it is still the same rectangle, same square, and it will stretch by 2. So the result will be again 1 by 2 rectangle, but it will locate it where? It's not going to be located right above. Where is it going to be located? Remember, the stretch is vertical. Another description that I used was it stretch away from the x-axis. The x-axis is not going anywhere. Okay, so we are, even though the stretch is all directions, but it's as if we grab it by 2 ends and stretch it in such a way that the x-axis remains the same. It's as if it is nailed, which means where what that blue rectangle, where should it be located? No, I'm still talking about the stretch. Yes, this vertical stretch by 2. Well, the bottom of the square lies on the x-axis, which means that it's not going anywhere. The top is not, so the top will move, but the bottom won't. Okay, so this is the answer. Okay, like this. Stretch vertically, and if wherever you put that rectangle farther away from the x-axis, it will be more and more pushed away. But if I put it say on the x-axis like this, it will turn once again. It will turn once again into 2 by 1 rectangle, 1 by 2 rectangle. That will happen every time. The location will vary. So this is what's going to happen like this. right? Stretched away from the x-axis with the x-axis remaining intact. Okay? So one more example. So if I put it over here, then the bottom is at the level of 2, which means that the new bottom will be at the level of 4, right? And the top was at the level of 3, it will become 6. Okay, it is dead. Okay, so that is your stretch. Vertical stretch. So this happens to be stretching in both directions, and you realize that whenever I have the same pictures below the x-axis, they will be stretched in the down direction. So that's the dissimilarity from the shift. If it is a shift, everybody's moving in the same direction. If it is a stretch, the ones lying above the x-axis moving up, the one below moving down. Okay? So the stretch is a tricky one. The rest are not. Well, maybe let me illustrate the flip one more time. So let's look at the first operation, the flip. Okay? The horizontal flip, and we'll see. So if there's anything tricky there, not really. The stretch, I think, is more complex. But so if I have my rectangle here, say, then its flip about the x-axis will be about the y-axis. A flip horizontal about the y-axis will be on the other side, like this. That's a flip. However, using a rectangle is misleading because you do not see what you don't see. If I'm using a square, it is misleading because we're losing some information. What am I talking about? I'm talking about the mirror image. The mirror image of the square is the same square, so that's not very informative. This is what I have in mind. If I take a half a circle like this, its flip will be a circle but pointing in the other direction, like this. Okay, so that's the thing about flips, that it actually creates a mirror image, and so if you are using for illustration just something that has symmetry, such as square, then you might lose that information. Okay, so one more flip. What if my object lies on the or touches or crosses the y-axis? Let's say, how about this? What's going to happen? It will be reversed, yes, but it will be like pivoted on the x-axis, on the y-axis, like this. So, okay. So the main challenge is because I have to do it plotted on the screen. If you do it on a piece of paper and then you just start flipping it, you can see the effects of this very, very easily. The previous example is more challenging because it's not as easy to find a piece of like a sheet of rubber that you can stretch proportionally and see the effect of these transformations. But at least flips and shifts are easy that way. Okay, so once again, illustration of let me sign a little. So this is a vertical stretch. And this is a horizontal flip. Okay, so just a couple of examples of what you might have to face when you carry out those operations. So there are just so many combinations that I don't want to look at them one at a time. But at least what came up just recently is what if we try to carry out one operation at a time, but with something more tangible, or something more relevant, rather. So this is all interesting of what happens to the plane under these algebraic operations. They are compositions, so if you know how to flip, stretch, and shrink, then you can combine them into anything you want. But our real interest is what happens to graphs of functions. So let's look at a few graphs and see what happens to them under these 6 operations. Okay, so graphs, transformations of graphs. So at this point, we're not talking about yet about the what happens to the function itself. I just want you to see what happens to graphs of functions as we transform them. Okay, so let me take a parabola, which is the most popular. I plot the standard parabola, and I'll carry out those 6 operations on it. So let's say it's parabola. Okay, so now so like I said, there will be 6. I'll have vertical, I'll have 3 verticals and 3 horizontals. 3 vertical and 3 horizontal operations. Okay. Okay, so these let me start with the vertical. Shift, uncomplicated. So shift up or down. The exact same shape. So I could just take it, copy, copy, paste, and I'll just do what happened. Okay, and that's what I do. I just put the old picture over the new one. Okay, so as you can see, the old axes are still visible, but the new ones too. Okay, so you can see what has happened. It's a shift. So let me mark the new axis here. So these are the new axes. Same exact shift. So same exact shape. That's the key to remember that the first 2 do not change the shape. Shift and flip, you can do it with a piece of paper. However, if you're talking about stretch, it is a piece of rubber, and the shapes change. Okay, so this is the shift. Now let me do the flip. Okay, so there is a flip here somewhere. Flip. Flip. Okay, I place it over the. Try this one. I'll place it over the new one. Like this. Not hardly perfect. Well, I hope the idea is there. Okay, so these are my axes. The old axes are still stick from underneath. So the y and the new y, the new y and the old axe are here. They're in blue, and the purple ones are the old ones. So let me mark them too. So this is the old y and the new y, and the old x. The old x is pointing still in the same direction. Okay, so that hasn't changed because the flip was vertical. And finally, the stretch is also complicated. I place it over the old one, and then I just stretch it. But still trying to keep not just stretching, but this is a stretch, but it's not good enough because I still have to align the x-axis. I'm stretching in both directions. So in order to make that, this is all the picture has been stretched, but it has to be placed correctly. So the x-axis, x's, the old and new, have to be aligned like this. The y-axis too. Okay. So, so these two are pretty much the same, y and y and x, because they are infinite. So the stretching of them does not change nothing about them. As a set, it's the same set. Okay, so you probably can see that what has happened to the graph of the parabola. So the vertical stretch makes it taller, but since it's infinite, it doesn't really make it taller. So if it's infinite, it remains infinite. So that's not a real comparison. So let me put one on top of the other, so that would become more descriptive. So I'll take the old one. I'll take this one. Okay, and I'll put the new one too over it, the stretched version. Okay, so well, I don't know if it is clear what has happened. So certainly it appears like it has been lifted, but the original one has been lifted. But you can see that it has happened non-uniformly, because nothing happened here. So it was at 0. Whatever lies on the x-axis does not move under a vertical stretch. Okay. In the meantime, as you move away from the origin, there is some stretching starts to appear, but not only that, it grows. So the actual movement of the points on the graph will increase as you move away from the x-axis. Proportionally, it's the same number, but because you are located so close to the x-axis, it might be, the difference might be negligible. So if your location was 0.1, your new location is 0.2. So the very small shift. But if you are at 10, then your new location is 20. So you can see the difference. Okay, so you can imagine what happens if we continue on with this picture. These two will start to separate from each other more and more like this. Once again, it's the same. It's a shape. Well, the shape is not the same, obviously, because the other one appears to be slimmer, and I do prefer to call it slimmer than taller, because the height of an infinite parabola is meaningless. Okay, so these are our three main operations. This is the comparison. Now, so this is all vertical. I'm sorry, horizontal. Now, no, it is vertical. Okay. Now the horizontal. Starting with the same picture. This is my picture again, and now I'm just doing horizontal, and that will be very different for one reason, because well, there is no symmetry here between x and y, and my parabola, as you can see, pointing upward. So let me try to click here. So that one is the original. Okay, that's the original parabola. And now I'm going to carry out Fourier transformations in the horizontal direction. Okay, the shift is easy. The shift is easy. It's not really different at all from what we just saw. Horizontal shift. Okay. Oh, what the hell happened? Okay, let's try again. This one, overlay it. That's a shift. As you can see, what has happened, we lost the symmetry. The vertical shift preserved the symmetry of the parabola. It still was the y-axis was still the axis of the of the parabola. So in other words, the left branch, just like the one on the left branch is the same as the mirror image of the right branch. Okay, so this time we would have lost that, even though the symmetry is still there. It's just not, the symmetry lies elsewhere. The axis is this time it is somewhere else. Right, so the shape is the same, so the symmetry has not disappeared, but it lies elsewhere. Okay, the second one is the flip, about what's going to happen. What's going to happen if I flip it? It will look exactly the same, right? Because of what I just told you, because of the symmetry, there will be no difference. There will be no difference, just to demonstrate that. Well, we'll see how good is my hand. Okay, so I take it here, I put it on top of it, and now I'm flipping it. I'm flipping it horizontally. Let's see if it is still visible. It's pretty good. So I flipped it, and it matches more or less with the rest of the curve. So so the left branch became right, and right branch became left. So roughly that's what it is, and they overlap each other. So finally, the stretch. We already did it, so it's not entirely new, but it is gonna. So this is my stretch. Okay, so I just stretch it horizontally, and then I overlap it on top of my new XY axis. And as you can see, that's what we have here. The comparison is the same, pretty much the same as in the last example, except, well, it is worth doing it. So let me try to do it and overlap the two to have the comparison of the stretched and non-stretched versions. So we can similarly analyze the. That's not the right one. This one. Okay. Copy, paste. Okay. I am overlapping the stretch and non-stretch versions. Okay. So the way it progressed is this, from the narrow to the wider. So it is wider. A good way to describe it is wider, but even though, in a sense, it has infinite width. It has infinite width at the end. But on each level, the parabola has become twice, or whatever the proportion is, roughly 60% or so, 6% wider. So that's the comparison. Okay, so this is the second half. The first half is the vertical. This one is horizontal. Okay. How did I lose it? Half of my parabola over here. Okay, so now, so that's what we started last time doing this pretty much. So let me review it for you. Okay, so we started to develop some rules for these transformations, algebraic rules this time. So these are the three rules that we have, and these three rules are apply entirely to the vertical. These are also, I don't know, H1, H2, H3. Three rules of vertical transformations. Okay, so as you can see, it's very predictable. It is what you'd expect for the function to happen. So we are not just transforming the plane anymore. We're transforming the graph of a function, and we see what is the formula behind that new function, and that's a new formula, right? So vertical shift, what we just saw, what happens to the function? You just add k. Vertical flip, you just multiply by -1. Vertical stretch, you multiply by k. These are the 3 examples. Okay, but we also saw yesterday or on Monday this tricky example of what happens if we think we are stretching the horizontal. We think we are stretching the x-axis horizontally, but the end result is not what we expect. So if I replace x with 4x, we know what this means. It means that the x-axis has been stretched and the plane has been stretched horizontally. But now, if I look at my function and carry out this transformation and just substitute into my function, so I had x squared, and I replace it with 4x squared. Okay, so this seems to be a stretch, a horizontal stretch. But now, what has happened to the graph of the function? So compare x squared and 4x squared. What has happened to the graph? Actually, I had 2 here, not 4. What has happened to the graph? 2x squared. What kind of graph is this? No. It is stretched. It is stretched, but vertically. It is stretched vertically, which means that it is shrunk horizontally. Which means that we are in the place that which is goes against our previous analysis, which says that when you replace x with 2x, we're supposed to stretch the x-axis horizontally, which means that we stretch the whole xy plane horizontally. But the end result with this is horizontal shrink. Okay, so why it goes in the opposite direction is to be explained, but you can. So until we start the next topic, we probably won't be able to explain that rule. We'll just have, for the time being, we'll just easier to just memorize it that everything goes in the opposite direction when we do horizontally. The shrink, you add 2 means that everything shifts to the left, not to the right. You multiply by 2, everything shrinks by 2, except for the flip. Flip remains the flip. Okay, the midterm. So midterm is it's the 5th. Okay, so okay, maybe next time. Okay.